Okay, so I will be discussing about winds from AGNs. Okay, AGN will be used in a very generic term, so we will be talking about any kind of outflows from compact objects. I mean, that is the basic theme. And these compact objects will have masses more than 10 to the 6 solar mass or so. So that's the definition of AGN for us. So I think any talk, first thing you want to ask is that after hearing the title, you have to ask why. Come on, why study AGN outflows? And I listed some of them as I thought about. I think one of the answer to any time when somebody asks why are you studying is that we have to study this particular aspect on its own, because that is why we are here. You take any topic, you want to study it for the sake of studying that thing itself. So first thing is that you want to understand kinematics, dynamics, nature and origin of the flows, because that is generic term. Like, you don't have to solve cosmological problem or you don't have to solve fundamental physics problem. You can simply understand why this object is emitting wind, and if it is emitting, why the wind is in a particular way. Why can't it be something different? Okay. If you go deeper, you want to ask what is the role played by hydrodynamics. So it's a simple hydrodynamic flows, but we know that AGNs are very intense emitters of radiation. So are we talking about pure hydrodynamics, or we will also have radiative hydrodynamics? Of course, if you do this and if you do this and if you don't solve the problem, we know, since we are doing astrophysics, we put magnetic field, right? And magnetic field and turbulence. So basic question is, how will we understand within the parameter space available to us to solve astrophysical problems? Of course, more generically, what we want is that first we want to understand what is a flow. Having understood the flow, we want to know where the flow is located. Is it close to the central black hole, or is it in the narrow line region, or is it in the broad line region, or it is outside the interstellar medium of the galaxy, or are we talking about of a flow which is going up to the halos itself? This is a tricky problem. It depends on how you observe the flow. Okay, these questions can be answered. We want to know the geometry. We want to know the covering factor. Covering factor has different meanings, because even though we listed all of them, if you ask people to construct the model, first thing one can envisage is the spherical. Because we know every curve can be a sphere. Similarly, every object can be a sphere. If you are worried about third dimension, it can be a circle. Okay. So basic idea is that you want to understand what fraction of this flow is actually covering the central engine itself. We want to know omega by 4 pi if you are interested in that term. Of course, we also would like to know stability. If I am seeing a flow, how long the flow can be exactly like how I see, how long it can sustain that shape and kinematics kind of thing. So we want to know stability. And if you are talking about stability, you may need to understand what kind of forces which are acting on the flow, whether the flow can be confined within these geometries. Of course, if you are going to study any astrophysical flows, one thing you want to ask is that what is the chemical composition of the flow? So you want this understanding chemical composition tells us that what kind of in situ star formation which is going on in a region where you are experiencing the flow. Okay. So especially these black holes or whatever AGNs are going to probe very central regions of objects, we can ask the question, if I am interested in understanding the history of star formation in the very central regions, I should be able to make some progress by looking at the composition of outflows, right? Chemical composition of outflows. Of course, we want to know what is the connection between general starburst which is occurring over the galaxy and the AGN which is growing in the very central region. Right? Of course, these are the things which is there. And I'm sure that Pratik would have touched upon these things. In addition to that, sometimes you do, this is the sequence, right? First thing you say that you study the object on its own, because you want to understand basic physics. Second thing is that you want to understand this object in its astrophysical setting, what all this object can do it. The third thing is that just because this object is there, somebody is getting affected, right? This is like saying that your research can go up if your colleagues are very good, and it can go other way around also. This is what is known as feedback. Exactly like this, a quasar in the central region of the galaxy can produce positive or negative feedback to the whole galaxy itself, because the amount of energy, a luminosity a star emits per, a quasar emits per unit time is equal to the average luminosity of the whole galaxy. The only thing is that locations are different. So you can, energetically you can say I can have feedback which can connect. The problem is that one is occurring over a size which is between us and the sun, like a AU scale. This is what is the AGN maximum energy generation occurring, but we are talking of kiloparsec and megaparsec scale over which this AGN feedback has to operate. Okay? So you want to understand whether these outflows trace birth of a new AGN. If you believe in a region where AGN is formed in a dusty region, when it forms, it shreds the surrounding material around it, and it could be a wind. People also talk about heating and enrichment of intergalactic medium by these quasar winds. Okay, if you are heating intergalactic medium, you can also heat intra-cluster medium. Okay, so that's the question one talks about, nice pictures one see when you look at the clusters, the holes and radio emissions in them. Of course, most of the interesting problem of galaxy formation is that people find that the very massive dark matter halos are very less efficient in forming stars. You take big halos, you find them, the star formation has to be very slow. Otherwise, you will not produce the observed luminosity functions of galaxies. So, of course, what you have to do, somehow you have to go and suppress this efficiency in which stars can be formed in big halos. I think nobody has a clear-cut answer. Again, like this thumb rule, dark matter, dark energy, magnetic fields. Now people say that wherever you don't understand how to suppress star formation, you put AGN feedback. And I have not understood somebody clearly demonstrating what they mean by AGN feedback, because it has several manifestations. It's like Ganesh, it can be everywhere. So high luminosity end of galaxy luminosity function, if you want to understand, you should have a clear picture of how AGNs operate in different black hole, different dark matter halos, and how the growth of black hole influences the growth of stars or suppression of stars. Okay. These are all big things. Of course, this workshop you are going to hear from experts on all these topics. I'm going to deal with very simple things. Okay. So what are we going to talk about? So I have been given a title, very nice title, saying that in multi-wavelength, right? Because I don't work on multi-wavelength. So I put one slide. I will say that this is what happens in multi-wavelength. And I will go to the wavelength of my interest and say that you do the same thing in other wavelengths, you will get the results. Okay? This is a simple strategy. So I satisfy the requirement as well as I am confined to what I know. What do you mean by AGN outflows? It's very easy for us to say all sorts of things. I will see outflows and all. But it's very difficult for us to actually detect outflows. Because these outflows are going to originate from very low density, high temperature gas. If you want to really detect them, we don't have any instrument to detect directly. Now at present, at least it may become possible in future. So how we are going to detect is that we are going to detect these outflows in the form of absorption in the spectrum of the AGN itself. If you take the spectrum of this AGN in X-rays and you find an absorption in X-rays, and if it is broad absorption in X-rays, we will call it as warm absorbers or hot absorbers. If you see it in UV, you will call it as UV absorbers. In optical, you will call it as broad absorption lines, and call these quasars as ball quasars. Okay. So in principle, outflows are detected in optical FUV regime. This is basically far UV and optical regime, which gets shifted to optical wavelength when you look at quasars at higher redshifts. These outflows reveal themselves in the form of what are called broad absorption line quasars. I will spend some amount of time on this. These called ball quasars. You can also see outflows in forms of some part of narrow absorption line systems where you find that the absorption redshift is extremely very close to the redshift of the quasar itself. In some very rare cases these days, one is detecting around quasar, you find that outflowing Lyman alpha emissions, right? You see this outflowing clouds fluorescing due to the quasar light itself. Okay, this is basically optical regime one is going to talk about. I will spend time on first two things, and I will tell you like whatever I listed in the first slide, how to find the location, how to find the physical property of this thing, we will go slowly. As I explained to me in the X-ray regime, explained to you, in the X-ray regime, you have warm ionized absorbers. This is basically, physics-wise, it is exactly same. Only thing is that ionization state is elevated. Now you are going to be seeing absorption lines produced by even more highly ionized gas compared to what you see in FUV regime. In radio regime also, like one is now picking up small collimated outflows and jets and associated broad H1 absorption. Okay, I have been involved in two of these things. One is that studying optical FUV regime and doing a bit of outflows in radio, because of course staying so close to GMRT I can't resist myself from using it. So we will start with associated absorption with 21 centimeter lines. Okay, so warm absorbers, basically this, whenever you talk of lines, outflows, what you are saying is that you are looking at outflows where your photons are getting absorbed, because of which continuum of the quasar will have a dip, right? So the dip can be produced by absorption happening between bound states, right? Bound transition. This is standard absorption line. For electron goes from ground state to upstate. When it comes down, it gets diluted by 4 pi factor. You find absorption line. You can also get absorption by ionizing the gas itself. The electron gets absorbed and it goes to infinity. When this happens, you produce edges, because all photon above this energy will not be seen. The edge will occur exactly at the resonance for the ionization energy. So these are called edges. Why I don't spend much time on this is an introductory level talk. I am not supposed to do big things, because this is left to the experts. What you will find is that in X-ray, because the resolution is so poor, even though advancement is so high, it is very difficult for you to distinguish what absorption you see is coming from sequence of narrow lines which are blended together, or it's an edge. So it's a technically correct statement, but we need not worry about it. We can just say that X-ray absorption along the lines. Okay, now I move on to just to give an example of how one does associated absorption. This is one of the cases. This is one of the absorption we have detected recently. What you look at is that you look at a radio source. This radio source is almost like a point source. Don't look at it now, we will come to this later. Radio source is a point source because its resolutions are poor in general with standard interferometers. We look at this object and try to look for 21 centimeter absorption at the redshift of the quasar itself, and you find this absorption, and you can see that this absorption is, this is the systemic redshift, and anything you find here, this is coming from the outflowing gas, the gas which is outflowing. And it is seen that now typically 40% of compact radio sources, if you go and observe, you find H1 absorption at the redshift of the galaxy or quasar, which radio galaxy or radio quasars, right? And what one can do in radio is also very good. If you are very lucky and if the frequency is in right place, you can go and look at the VLBA image of this object, and this is the VLBA. In VLBA, this radio source split into two, and these scales are millisecond scales, and you see them splitting into two, and you can actually take spectrum towards this and this, right? This is not possible in any other regime. So this is the thing, this is the spectrum. What you show here is the spectrum obtained with WSRT. This is exactly the same. This is the spectrum observed with GMRT, which is shown here. You see that both of them are same, it's reproduced, because the source is compact. Whereas if you go and look at the spectrum on top and spectrum bottom, what you are seeing is GMRT is the combination of these two, right? Because you don't resolve. You look at the absorption produced towards this, and you combine and see the combined spectrum. But in VLBA, you split them, and this is what is the thing, right? What you say is that this is towards this lobe, and this is towards this lobe, and this coincides with the radio optical counterpart, okay? And you can clearly see this. Towards the central region, you see this blue shifted absorption. And this has a velocity of something like 600 km per second. It's like you see that this is an outflowing gas with 600 km per second. And what is interesting, if this outflowing gas is 4 pi steradian covering everything, you should see between these two lobes, right? Between these two guys should show the same kind of outflowing signature. What is interesting is that even in radio, when you detect outflows, it seems that they are very collimated. Even at the case of parsec scales. It's very interesting, right? I started with this, I thought like I'll start with something very interesting and very revealing, because here you don't have to do anything. You look at two sources, if a wind is covering both the sources, you should see same amount of absorption. You see a strong absorption towards one, you don't see strong absorption towards other, and it clearly demonstrates what kind of scales involved in the problem. I think this can be extrapolated to as many sources you want, as long as this source live in a region which is RFI free, which is very difficult to find and very bright. Okay, what have we understood from associated 21 centimeter absorption? Roughly 30 to 50% of radio allowed AGN show absorption, H1 absorption, at the redshift itself. This is very strong thing to see. If you confine yourself to compact sources which are sizes of the order of parsec scale, and you find that the detection rate slightly goes up. Absorption profiles are typically contain various things are there in absorption, because you have to remember the problem with absorption is like saying that here is an animal, I give a color of the skin in one point, it is black. Now identify the animal. This is the problem, right? When you do absorption line, you throw a sight line which is through one point, and you are probing a three-dimensional object. Okay? This dark spot could be an ant, It could be an elephant, it could be a donkey which is dark. So that's the problem. This is up to your imagination. That means that even when I am confidently saying you can detect outflows, you have to define what do you mean by outflow. So if you look at an absorption system in any quasar, it can be narrow, or it can be very broad. When it is broad, you know that it cannot be thermally broadened. So you have to go to the width of the line, which is large enough so that you can say that this width is dominated by the flow itself. There is a velocity gradient in the gas that is contributing to this. So typically any width which is about few hundred kilometers per second and smooth profile, you will think that it cannot come from a cold gas which is sort of a part of a disk or a part of a galaxy or whatever. Okay. So if you do this and screen these 30 to 50% cases, you find that 5% of radio loud AGNs show signatures of outflow, which we can with confidence say that this is outflow. This 5% should be considered as a lower limit because I'm screening, I'm going to the extreme cases. So they can have velocities up to 1000 kilometers per second. Okay. So other rest of them which are seen at the same redshift may be related to cold infall, circumgalactic medium, blah, 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 blah. But what we are interested in this meeting is to study about what happens to these outflows. And outflows are typically in radio galaxies. It is like 5%. Okay. Why this 5% should be considered also as a lower limit is because we are using H1 line. What is this H1 line? H1 is neutral hydrogen. In radio, you are using what is known as spin transition, 21 centimeter transition. This is 1s ground state split into hyperfine states. And the ability, our absorption line strength depends on what is the quantity called spin temperature. That tells you the relative population between these energy levels. If spin temperature is very high, most of the electrons will be in the excited state, which means that the amount of absorption coming from the ground state will be less. Other way of saying, optical depth will be inversely proportional to what is called spin temperature. That is the first thing. Of course, the most important point is that the gas has to be neutral. You are saying that there is an outflow, things are going with very high speed. You want to keep these blobs which are tracers of this outflow till cold and neutral. So these two means it is not a generic problem. If you have an outflow, it is not guaranteed that you will find H1 everywhere. So because of which we will say whenever you find H1, at least you are detecting some fraction of it. Okay. This is why we say this issue. Of course, since you will be hearing a lot of radio astronomers are around, one of the questions one keeps asking when one finds this kind of flows and flow geometries, he says that what is the effect of orientation versus whatever lifetime, right? This is always a problem. Young sources or old sources or young sources or beamed sources seen in some angle. This goes on and this will go on. I think it was there during my PhD and I'm sure it will be there during your student's PhD. Okay, now coming on to broad absorption line flows. And what are broad absorption line flows? This is what I will concentrate in most of my talk. If you look at a quasar spectrum of distant quasar, about 20 to 30% of the quasar spectra doesn't look like a simple power law which you expect from this curve which is shown here. This is what we study in textbook. We say that simple power law with broad line region, narrow line region, blah, 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 blah. It's true for 80% of the sources, but remaining sources you find this kind of broad absorption lines. This is why these quasars are known as broad absorption line quasars. And these absorption line can come from any physics you can think of. It could be due to exactly like same reason. You are doing absorption lines. You can think of all sorts of geometries which can be consistent with the absorption line you are studying. Okay, it could be like a stellar wind. It could be like a supernova or nova kind of thing, and it could be like a byproduct of a explosion which has occurred close to the quasar itself. We never know what is causing it. It cannot be in flow because most of the time the velocity offset is always in the blue words because there are high ejection velocities, velocity going up to 0.1 c. I will show you example. So now onwards you will see that why these things are special. These balls can have very large ejection velocities, and you can give an example here. This is the region where you expect nitrogen phi and Lyman alpha emission from a quasar, and you find a nitrogen phi absorption here. And I estimated the velocities, and velocities can be up to, this is not coming up, kilometer per second. It's like 0.1 c roughly, right? This gas is actually at the redshift of the quasar, but it is shown at a much lower redshift because of the very large ejection velocities towards us. Okay, I think this cannot come from any other thing, and you have to envisage that it is very close to the quasar getting accelerated to much larger velocities. Of course, if you look at it, this is already a very high resolution spectra. But in most cases, in half of the quasars, this is the typical spectrum you get from SDSS or whatever, right? And if you go and split it with Eshel spectrograph like VLT UVS, you will find that this whatever you call smooth flows splits into very, very narrow, large number of narrow components, which means that one thing we know, large velocity flows exist, and on average they have so smooth profiles. The velocity, absolute velocity shift can be as large as 0.1 c, but these are not smooth gas distribution. It is not like a free wind from a model where you expect the density profile to be uniform. It seems that there are embedded clouds in this. You can think of like a water flowing with boats floating on that, right? Or whatever, maybe like some foam or something floating on that. So you can think of these clouds as a tracer of the underlying velocity field, which is pretty wide. So that's the way to look at it. But it's even more shocking. This velocity where these lines occur is not random. Okay.
Srianand,
yeah.
What is the definition of broadness? I mean, at what width it's considered to be broad line?
So usually observational definition 1000 km per second, but even 100 km per second can be broad, because if you don't see thermal broadening signatures, these things are quite broadened by the motion itself. Wherever you find a signature of profiles broadened by bulk motion, you can call them. But for statistical purpose, people define it as 1000 km per second. Okay. Next thing is that, okay, this thing didn't come out well, but nowadays with HST COS, one is able to detect not only this kind of carbon 4, silicon 4 and low ions, now we are able to detect neon 8, sodium 10 and things like that. So these are pictures which, I'm sorry, this didn't come out well, because here basically we are showing absorption produced by neon 8, so 7 times ionized neon, and this part will be sodium 10. Okay. So these things are very much in the FUV. 700 angstrom is the rest wavelength. Now that HST can reach 1500 angstrom, if you go to redshift 1, these lines come into the optical window. Okay. Now the question we want to ask is that what physics drives the flow? If the flow is there, we know flow is smooth. Flow is also having this kind of structures. What physics one can do? In fact, things can happen with simple technique. What people did was people took all the quasar spectrum, just stacked all of them, redshifting to the redshift of the quasar. Just look at what is the average profile. Okay, average profile looks like this, and basically you find this goes by the name double hump profile. Average profile is dominated by some sort of a double humps, and you can ask what is the separation between this and this. It seems the separation between them is exactly the velocity separation between Lyman alpha and nitrogen 5 emission lines. It's very tricky. The velocity separation, average velocity separation between two clouds you see is exactly like a wavelength separation between two ions which are of interest to us. If you have done little bit of laser cooling or laser thing, you can actually trap an atom, trap an energy level by bouncing them between two frequencies. You can laser confinements one does. This is what exactly happens. Here what happens is that this flow is dominated by absorption of photons in various forms, and whatever photon momentum is there, this is what is driving the flow. This goes by the name radiatively driven flows. If radiatively driven flows are dominating, then you can get this kind of configuration where absorption is dominated by nitrogen 5 and Lyman alpha. If you close one of them, if you remove nitrogen 5 from there, half the momentum will go down. If you reach this case with gravity, you will be able to adjust this flow and get the velocity structure exactly like the way you want. Okay. I know that it has gone above most of you, and remember this name and look at in Google. It is known as line locking. You search in Google and find out what is line locking. Line locking is nothing but a flow velocity can be locked to a frequency of your interest by making sure that the flow is dominated by these species. Okay? I will give you an examples of line locking as we go on. So it seems that 20 to 30% of the cases one sees these signatures, and it means that line driven acceleration is an important physics one has to worry about. Radiative acceleration one has to worry about it. But one will say when something is moving at a rate of 10,000 or 20,000 km per second, how will you make sure that there is no shock in the medium? Because your Mach number is so large. How can you avoid shocking a region? Now the question is, maybe it is shocking. It's so shocking that the gas is gone to much higher temperature you are not probing. So the fact that you have no signatures of shock simply implies that you are blind to that. Okay, so that's why I just put it. So what is the thing to carry from here in this slide? Okay, now outflows are dominated by quasar. They are smooth and high velocities. They appear like minute structures where you at higher resolution they split into smaller components. And even at the broader scale, we have a signature that this is not random, it is driven by radiative forces. Other interesting thing one notice is that these absorption lines, most of the time they don't go to zero. So this is a typical continuum. This is how the quasar should have looked like if there is no absorption line. But what you see is that you see a strong absorption line. What you expect when the absorption is perfect, this region should have gone to zero, right? All the photons are absorbed. But it doesn't go to zero. Not only that, very interesting thing happens that if you look at the bottom, it has a shape, and this shape exactly mimics this shape here. It's very interesting. You have to imagine a bit. There is a configuration. We have a quasar and it is ejecting some material. Quasar light is absorbed by this material. The quasar also has other regions like broadline regions which are there. Broadline regions are emitting photons from all over the place. And this region is much bigger than what is the region covered by this absorption. This light directly comes to you. Some bit of broadline region light directly comes to you. This light, what you are seeing in the bottom, is a light which is not going through the cloud itself. It's coming from the sides. So which means that the cloud is compact. It covers the central quasar, but it doesn't cover the broadline region. It tells you the location. This goes by the name partial coverage. So what are the names you have to remember? I think in lecture, if X-ray outflow, anybody says, they will say partial coverage. It's very difficult to demonstrate in X-ray, but this is the best demonstration you get in UV, because you can see nicely that pattern is repeated nicely here. So this one has to worry about. One has to worry about partial coverage, and if you understand this partial coverage, you can find the locations. Okay? Ball quasars in X-rays. Now you can ask, all the quasars, most of the optical quasars are loud in X-rays. Is these ball quasars loud in X-rays? They are not. Usually ball quasars are very weak in X-rays. So of course you can say, if something is not there, it's very difficult to write two kinds of paper. One thing is there that the source is not there. That's one set of paper. Second thing is the source is there, somebody hide it. Okay? So this is the problem. I think now that you are sleeping, I can give you how theoretic interpretation. Apparently, one guy said that here is the picture of cow eating grass. And the picture was exactly like this part, it was white. So people asked, where is cow? Where is grass? I don't see it. So this guy said, cow has eaten it. Where is cow? After eating it has gone away. so it's exactly like this. So when you don't have X-rays, you have two things to do. One is you can say like, these ball quasars are intrinsically X-ray weak. Whenever there is an outflow, for some reason they cannot emit efficiently in X-ray, right? The second thing is that they are emitting as efficiently as any other quasar, but these outflows, they simply absorb these X-rays. And this can be tested. And now what one believes is that most of the cases, the lack of X-ray is not due to absorption, it is due to intrinsically different property of ball quasar compared to rest of them. At least in X-ray, that is the consensus one is reaching. Of course, one thing you can do is that if you go to anybody, I think Pratik may be one of the guys, you go and tell him, make me a model for outflow, he will make you a model for outflow. But the problem with this model is that it will predict a lot of interesting things. It will say that at some regime, there will be acceleration, some regime, the gas will reach a terminal velocity. Even if the flow is in an unconfined medium, it has to be accelerated from 0 to some velocity, and then, so if one is saying that I'm studying the outflow, first thing you will ask is that do you see a signature of acceleration? Today the absorption should be here, after some time it should be moving in the wavelength space. Absorption meaning velocity is changing meaning you should see change in the wavelengths. So one can go and ask whether you find such things. So we have been monitoring this thing. This is one of the things we are doing for last 7-8 years. You take all known ball quasars, you systematically go back and keep on observing them and see what happened to these outflows. Do they stay exactly like this, or do they change in shape? Do they get accelerated? Do they get decelerated? Because it's also interesting to see outflow going back. It is very nice to have such a model where something goes and comes back. It's like our oscillating stars. Do we have such things? Okay, here is an example of X-ray loud ball, which is basically whom and his student were involved. And you can see that it is one of, I'll answer you later because I will finish this part and come to you. Okay, so you can see this black part is a spectrum taken some time back. Red part is the spectrum taken at the later epoch. Arrow shows the centroid of this absorption. And what one sees is that there is a change in the position of the absorption, and it is basically, this is the kind of signature one looks for acceleration. Okay, acceleration in modulo. But this change is occurring in an interesting way. It is actually going inwards. Other way of saying is that as a function of time, line of sight velocity is decreasing. Okay, but what has happened now? Whom will be seeing it for the first time, I suppose? This has disappeared now. This quasar, which was supposed to be a X-ray allowed Ball quasar, has become a normal quasar now. And basically the model, what you need is that you need a time scale over which the guy was accelerated to high speed, and you see that velocity going down and now disappearing. So we have a model for it. I'll explain to you later. There is a second kind of thing which we are seeing now, is that again it's one more case. It's a bit complex, and you can see there is no absorption in this position. There is a small absorption which is appearing. Again, this absorption goes away. There is an absorption which appears. This absorption goes away, not there, appear, slightly beginning to disappear. And we're beginning to see what is known as recurring absorption. It's very interesting. It means that, like, this is seen in OB stars. There they say that star is rotating, your outflow is anchored to the star. When outflow is towards you, you see absorption. After some time you get. If this happens, you can calculate the period. It is very dangerous to associate to period. This is why I'm sort of monitoring for, if it is associated to period, only place the flow can anchor will be the black hole accretion disk. It will be interesting to look at this physics behind. I'm just giving you examples of what one see in the outflows.
So, but why would you expect it to be periodic? So, it's suppose your outflows will be.
I don't expect it to be periodic, and I will be very happy if it is not periodic.
Yeah.
If it is periodic, it is very interesting. And it is periodic.
What would it mean actually?
This observation tells me periodic, at least to till now. Which means that this guy, for some reason, it is not always in your line of sight. It is coming back to your line of sight because it is coming at the same velocity. It is periodic, but it is appearing at the same place in the spectrum. So when I am through the flow, I get it exactly at the same place. When I am not along the flow, I will not find anything. So that's why I'm saying that it has to be anchored to something which is rotating. Flow cannot go like this, it will be too much, I think. One can think of like this helically moving blobs, but I think more realistic will be to anchor it to something and which is rotating.
Is it due to a filling factor lower than 1? Like there is a flow of clouds?
It has to be lower than 1, otherwise you will not see variation. If it is 1, you will not see variation. But filling factor is a strange quantity to define. Even I can, when it is on the line of sight, the filling factor can be 1. What do you mean by filling factor? Filling factor is with respect to your background. Your background is not uniform, I'm saying.
But I want to understand, is it a property related to the outflow or is it a property related to the flow density? Or it could be both?
It is a property related to the outflow.
What is the period?
It's of the order of 1.5 years. Its rest frame, it is 3 months or something like that. Anyway, I have to confirm these periods carefully. Period is a strong word. A repeating thing is much better word than, that's why I gave a name recurring. Recurring is much better because I need not preserve the same cloud. But this is like saying that in a street, you will find the maximum concentration close to the lampposts, whereas wherever signal is there. So the high density concentration where you will find, I can say close to the signal. When I find high density concentration of cars, I need not find the same cars. So periodic is a problematic, recurring is a much better word to use. And recurring that way is that blobs will spend more time in the velocity and space. This is what I am thinking in that way. So a curved motion can easily explain this. That is another explanation. Of course, third kind of variability one expects is what is known as photoionization induced variability. These clouds are in ionization equilibrium with the quasar itself. Quasar excites them. If quasar become faint and bright, this absorption can change. We also see them. Here is an example, and you see that the absorption which was like this become something like this, a dramatic variation in the absorption. You will immediately jump and say that it looks like a flat one, but it looks like double Gaussian. This is simple idea of saturation of lines. The column density, actually every time there were 2 clouds. In this epoch, there were most of them in the neutral form, or whatever you call, most of them in carbon 4. Now they would have gone to carbon 5 or carbon 3, we don't know. What is interesting is that we could monitor them photometrically, these quasars, And this is the idea. During this period when we have observation, we see that quasars have faded away, and one can clearly explain the fading of quasar and change in the optical depth are completely related, and this can be understood in terms of ionization change itself. Here the flow can be steady, nothing is changing, only quasar ionization changes. But of course, change in ionization can cause change in the acceleration. So that means when you have these small blobs, you should see a little bit of centroid shifting, which we see. Okay.
How much is the change in the brightness? I cannot read by it.
It's like 0.7 magnitudes.
Okay, thank you.
Okay, of course, there are also interesting cases which we are finding. One is that there was no ball quasar which has become this is what we call as transient balls. And we are beginning to see a lot of these disappearing and transient balls in this. And I think there is a paper which appeared last week in AstroPH on this. So now more physics question you want to ask is that what parameter decides this flow? You can now plot, this is the, again, I don't know, for some, I should have made thicker, this is distance related to that. I'll explain what I'm plotting here is the variability of strength of absorption as a function of various quantities. Here we are plotting redshift of the quasar, and it seems that most of our quasars are around redshift 2, and I cannot say that there is a statistical significance that high redshift quasars emit more varying outflows compared to low redshift quasar. There is no such things. The strongest indication comes from here. Here is the median, this is where what we plot is the ejection velocity as a function of variability parameter. A large scatter you see here when the ejection velocity is very large. The cases I explained to you, like whatever large absorption variabilities and all, typically occur in clumps which are having large velocities. Now it depends on what model you are interested in. If you are interested in large velocity occurring close to the central engine and then they get slowed down by the medium, it's you are talking about short time scales because the object itself is compact. But if you are thinking of some flow which is moving and reaching a terminal velocity and all the large velocities are occurring at the terminal velocity, then this could reflect the interaction of this flow with the medium itself. So it's very interesting to note this. Other place where we found is that when the absorption line intrinsically was very strong to start with, you find that very little variation in them. That is what is plotted here. When you find a strong outflow, you don't find much variation, whereas you find variation when the flow is shallower in the optical depth. Again, this is a subtle point. This is something to do with the way you analyze the spectrum itself. If the absorption is strong, you produce sufficient, when the cloud is having large number of particles, you produce sufficient amount of absorption. Making the number half doesn't change it because it's already saturated. Only part of the cloud is absorbing. Rest of them you do whatever you want, it doesn't matter. Okay. So last bit is same thing plotted like in a different units, but thing to carry is here. Variability is high at high ejection velocities. Variabilities occur over a characteristic time scale of 3 months. This is another quantity which is very important. Irrespective of whatever is the luminosity of the quasar, whether it is radio loud, radio quiet, X-ray loud, X-ray quiet, the strongest variability time scale is close to 3 years. I think this is the 3 months in the redshift. There is a weak tendency of radio bright quasar to show large variability, and what we found is that variability does not depend on quasar properties. You can measure black hole mass, Eddington ratio, you can do all these standard things which you can do with black holes associated with this outflow variability, whether it is varying or not, it doesn't depend on the black hole. Okay, it's very interesting.
So is that's very strange, right? I mean, shouldn't it depend on the accretion rate, for example, the disk or?
Why do you think it's so natural? So whatever you think is natural is wrong. That's what is the problem. Because in the sense that naively one expects that it is not matching with that, which means that your canonical way of thinking that high accretion rate meaning black hole mass and blah 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 and typically high outflow rate. I don't see why high accretion rate should be related to high outflow rate. Such models which try to unify this thing may be wrong. So basically this outflow may be generated by the geometry and what is driving the flow much more than the black hole itself. So it may be going into the variations you can come up with accretion disk properties. So, okay, properties of, I think I have said this before, but maybe I'll skip this. Now I focus a bit more on narrow absorption lines. There is a difference between these broad outflows, whatever you have seen, these are all very broad and these velocities are very large. You can also have associated absorptions which are much more narrower at the redshift of the quasar itself. You can do the same thing. But these things are much more interesting because in the case of broad outflows, whatever I said is sort of a negotiable arguments. You can say that how do you know it is inside the BLR? How do you know what is the density? How do you know what is the velocity? Velocity is measured, but all other quantities are inferred through photoionization models. Here you can actually calculate various quantities. I will go one by one. Of course, you can write down radiative transport equation. It's the same equation, right? I goes as I naught e to the minus tau plus. So what we do is that we can also say that this clump does not cover the full thing, so you can modify this equation a bit. You say that I goes as I naught into the fraction of gas, which is fraction of light which is going through the cloud, and plus whatever light which is coming from the surrounding. That means if you measure what is the covering factor of the region, you will be able to actually measure the intrinsic size of these objects. Okay. So I went little more technical. Probably I don't know how many of you, if you have done spectroscopy, you have singlets and doublets. You can have doublet transitions. When you have doublet transitions, the transition probabilities are fixed. You can use it to identify what is the hidden saturation and what is the level of covering factor effects. Okay, I'll skip it, but you remember that in principle, when you find these kind of lines, you can decompose these lines into different ground state levels, and you can ask the question whether transition coming from the same ground state have ratios which are consistent with what you expect from spectroscopic ratios. Okay, that allow you to, any inconsistency, you can use it to invert and ask what is the cause of it. The cause of it is most of the time related to the compactness of this thing. This is what one uses to get the size. For example, these clouds produce absorption only coming from accretion disk, but they still cover accretion disk about 70% area only, which means that these clouds may be very, very dense and compact. Okay, and you can use this equation. You can actually, I want to show that for whenever you find absorption, you can actually calculate covering factor, because here is a carbon for absorption, it is a doublet. I just want the take home message is that whenever you find absorption in this kind of well resolved cases, you can actually calculate each velocity, what is the covering factor of the flow itself. Of course, if you are very lucky, you will find a flow which appears like a train bogies, right? And you see this is one of the cases where you have, and you see that things are repeated. What I have done here is that I keep the absorption line exactly same, and I take it and move by this separation and plotted it as a dotted line. And you see that everything is just reproducing, right? I've just same spectrum shifted by this gap. So which means that it seems that it is like some sort of absorption which repeats. It's like carriage of train which has linkages. And this is the manifestation again of what I explained to as line locking. This is a very good manifestation of line locking where it says that the flow is actually governed by the radiative forces. Okay. So this is again easy to remember. If somebody shows a spectrum to you in future and you find something going like this, you just ask whether these separations are same. If you find separation between these troughs are exactly same, and these separations will be exactly the separation in wavelengths between those doublets of interest to you. So it's very nice thing, and I'm very excited about it because like this proof was first given by me, so I was very happy. Every time irrespective of whatever topic, I will show it. Right? Just to the other thing which is interesting for us is to find out what is the density. So this partial coverage gives you, and this line locking gives you the idea that cloud is small, it is driven by radiation. Now we want to ask that how small is the cloud? That's how small is related to what is the density and how much size it will have. Okay. So density can be measured by what are known as fine structure lines, and you know that each ground state, each whatever you call level, when you have splitting, you talk about hyperfine splitting. Similarly, we talk about fine structure splittings. The spin orbit coupling like that, angular momentum couplings will give you this. And we know that in hydrogen atom, you talk about splits of states into finer details, right? 2p, 2s, blah, blah. If you go to fine structure states, you can find splittings of, for example, carbon atom, neutral carbon, or ionized carbon. You will find fine structure states. Between fine structure state and this state, they are excited by infrared emissions. Usually the energy gap is very small. Whereas one can actually look at absorption lines produced by these fine structure lines if these states are excited. Basically, these electrons are excited by collision. They not only stay in the ground level of this fine structure, they are also in the excited fine structure states. So if you are fortunately in a right densities, you will find that this absorption can be picked. When you find this absorption, for example, silicon to fine structure, if you find a ratio of silicon to ground state to silicon to fine structure, you can actually measure the density directly. This is the density of the gas which is producing absorption. And these lines are very frequently detected, and you can use them to actually measure densities. So why, now you know why I ignored X-rays and concentrating on this, because you can find the location by partial, we can find the size by partial coverage, we can understand the physics by the way the lines are arranged, we can get the density by looking at these fine structured states. Of course, you will solve this by kind of local thermodynamic equilibrium equations, where you will take care of collisions, radiative excitation, and UV pumping. So this is a bit complex, but you can do it. And I give you an example. For example, for carbon 2 to fine structure level to ground state, this is how the curve should look like. You go and measure the ratio, and you put ratio and 1 sigma error. Wherever this line cuts, that will give you the temperature. And this cross-sectional ratio is plotted for different densities. Which density curve cuts here, if you know the temperature, you can solve for it. If you don't know, it is very good for physicists, because you don't worry about constraining temperature and density, you constrain what is known as pressure. So you can actually give gas pressure in clumps. Okay. So we said that time variability studies can be used, and you can also use time variability in yet another way. Another way of saying is that you are looking at a gas, this absorption line is changing. What is the meaning of absorption line changing? Amount of gas in a particular ion, along your line of sight is changing. How can it change? I can change the number of ions. If it is something, if for example hydrogen atom you take, if absorption produced by neutral hydrogen is changing, I have to change the amount of neutral hydrogen in the gas. How will I change? I will either ionize it or make more electron recombine it. So what is the characteristic time scale over which this change can occur? This is related to what is known as recombination time scale. Recombination time scale is nothing but how much time it takes for an electron which was kicked out of an atom to come back to that. This is the other way of looking at it. This is a new definition. Other way of saying it, completely ionize the gas, let it go for how long it takes to recombine to become neutral. That time scale is known as recombination time scale. That goes as 1 over Ne alpha, alpha being the recombination coefficient, and this should be equated to the time scale over which variability occurs. So you know the time scale over which variability occurs, you know this quantity, you can calculate density. This is another way of calculating density. So this problem is very much trackable. You can calculate densities through 3-4 techniques. If they don't match, it tells you about the geometry. If all of them matches, it is spherical curve. If it doesn't match, you need a sheet or you need a filament. So that's the way you use all the probes to do this. Okay. Of course, what one will use is what is known as photoionization equilibrium. It is nothing but you expose this cloud to the background radiation and ask the question like how much of this gas is ionized, and then you can ask what is keeping this ionized gas ionized. Okay, how much time I have? About 10. Okay, comfortable. I have only 4 slides more. So basically this side what we have is, this is for pure hydrogen atom. You take hydrogen atom, number of hydrogen atom, number of ionizing photon, multiply by this photo absorption cross section, it gives you number of photoionizations in this side. This side you get number of recombination, it is number of electron, number of proton recombination coefficient. If you assume the atom to be highly ionized, Ne equal to Np equal to Nh, so you can write down this equation. You can solve this. You know the luminosity of the quasar. If you know where the cloud is from the quasar, we can calculate what is the flux from the quasar. We don't know the number density, and we can solve for it, right? That's how it is done. And this inevitably every one of you will be using. If you are not brave enough, you will use cloudy. If you are brave, you will try to write down your equation and solve. And soon you realize that the braveness is not very good. It's better to run cloudy. Okay. So this is the example of cloudy. So what you can do in cloudy is that you can take a cloud of some composition, put it in front of the quasar. You just either vary the density of the cloud or vary the flux coming from the quasar by just moving this guy outwards. This quantity is known as ionization parameter. Ionization parameter is nothing but number of ionizing photons, number density of ionizing photon divided by number density of particle. So you can take one of these things, carbon 4, amount of carbon which will be in carbon 4 is as a function of ionization parameter is given here. So if you assume a composition, you can actually plot how much carbon 4 column density I will measure as a function of ionization parameter, how much silicon to how much carbon to all these species. What you do is that you go to your observation, you measure all these column densities directly, you draw horizontal lines, and you find out what is the impact ionization parameter at which maximum number of this horizontal line cuts the curve which corresponds to that element. If I take carbon 4, curve is here. If observation is here, it will cut here. I think that this should be the ionization parameter I need. If you are lucky, for all species, the horizontal cut will occur at the same ionization parameter. If it doesn't occur, okay, no problem. You will say that this is a multi-phase medium. If it occurs, it is single-phase medium. This is okay. Well, we have to somehow write the paper, right? We will not give up after all these observations. Okay, come on. So Claudia also tells you whether physics, whatever we are talking, works or not. This is basically an incident continuum, and what is plotted here, what will happen if you choose one cloud, and now ask, this is the incident radiation, I take the radiation which is coming out and plot what happens, and you see that this is the beautiful transmitted spectrum. Transmitted spectrum in two different conditions. One case, in this regime, it is completely absorbed, and in another case, there is partial absorption. And I made this plot keeping in mind that it is two extreme ends. Here what happens is that here is completely neutral gas. Whatever you don't see here is completely absorbed by hydrogen atom only. It is nothing more than that. But here it is a highly ionized gas. Whatever absorption you see is coming from metals, carbon 5, nitrogen 5, nitrogen 6. So this will correspond to what X-ray astronomers call you warm absorbers. This will correspond to what we call as Lyman limit systems. Okay. This is what I wanted to say. So properties of narrow absorption line systems. 50% of Seyfert galaxies and 20% of quasars show intrinsic absorption at the redshift of the quasar or of the AGN itself. Most of them show excited fine structure lines. You know, when you have excited fine structure lines, you can calculate this excitation and find the density and pressure in the region. You have to solve this equation with combined equation. If you can't solve, you go to my paper. I have given the things which you can easily read out. Partial coverage, we explain how you can do. You actually see the bottom doesn't go to 0. Sometimes it traces the quasar emission itself. Otherwise, you can do it with doublets and use some standard spectroscopic technique. Very high degree of ionization which you have seen, which means that it has to be very close to quasar. Time variability tells you that these are high density objects because recombination time scale has to be short. Okay. And one thing I didn't mention, because that take me completely away from my main theme, is that whenever people measure metallicity, they turned out to be much more than solar. Even for redshift 6 quasar, when you find absorption at the redshift of the quasar itself, the metallicity turns out to be much more than solar, which is very dangerous. Redshift 6, you have not much time to generate stars, OB stars and all sorts of stars and do this. So it's interesting for us to ask this question, what causes the chemical enrichment in the very central regions of AGNs itself? This slide is for people who do cosmology, in case, on kinematic luminosity of AGN outflows. So having done all these things, can you make some statement about how useful quasar outflows to galaxy formation itself? Okay, I will rapidly explain what is the physics behind or what is the approximation behind. You can write down mass outflow rate through this equation. It is not very different. You are assuming a shell and you say that all the outflows are in a shell. This is known as thin shell approximation. And only thing is that we put a fudge factor, this C omega. This is basically covering factor. We say that it is no more a shell. It is almost like a shell with a smaller opening angle. This you can think of omega by 4 pi is the thing. Right? And what are the things we need? 4 pi r square meaning distance of the cloud from the center of the quasar. We want velocity you measure. This is quantity which we measure accurately. We know the redshift, we know where the absorption occurs, we measure velocity. We don't measure density. So mass density, first you convert it into number density into mean molecular weight and the mass of proton. And then what you do is that r square you split into r into r. Is NH into r. The density into r will give you a dimension of number per centimeter square, which is what is known as column density. Column density is nothing but number of atoms along your line of sight. This is measurable. But the problem is the column density of baryons is what you need. What is the meaning of column density of baryons? We need to know column density of hydrogen plus helium, blah, 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 which you don't probe. Even though you don't probe it, you have to predict it. How do you do is that you predict it through saying that I measure neutral hydrogen and I find out what fraction of hydrogen is neutral. I can correct for it. So this quantity is measurable. This quantity is measurable. I can measure R whenever I have a constraint on density. When I know what is the density, I can calculate ratio of number of photons to the number density of particle. So the density and radius can be accurately measured through whatever I explained to you. Fine structure lines you can use covering factor arguments and variability arguments. So now you can convert this into a kinetic luminosity. Okay, basically you divide by mv square, m dot v square, that is the kinetic luminosity. M dot is given here, and you see that it scales as column density r and v cube. So as long as you make minimal error in r, v is accurately measured, that has the strongest power. So this quantity can be estimated, and it turns out that kinetic luminosity in any realistic model is pretty high. You get 3 to 4% of Eddington luminosity from the black hole. So that means these flows carry, what you need for AGN feedback is something like 1 or 2%. We have 4 to 5% already available in the flow. But the problem is, if you want to make an isotropic impact, this guy has to be close to 1, right? Because you want to heat whole region. We don't want to heat some small regions in this. Okay, that's the first thing one has to worry about. The second thing one has to worry about is that where is the location? When will I call the feedback important for galaxy formation? If the feedback is destroying the narrow line regions and broad line regions, will I call it's important for important AGN feedback for galaxy formation? No. It has to go to at least interstellar medium. So that means only certain kinds of flows in quasar can last up to that distance. So that is the question, whether you can, whatever flow you see at 100 parsec, can you preserve the same luminosity up to kiloparsec? That is the question you have to answer. That's the last slide. I don't have anything more than this. Thank you very much. Mahadev, you asked a question. Oh yeah. you can't say no now.
So what could be the reason that the seaport has more fraction of seaport has outflow and less AGN? QSO is like 20%, seaport is like 40%.
Yes. Okay, so the question is, when you look at Seaford, I don't think we have color selections. We measured Seaford purely based, this is Seaford galaxy. Whereas to get to the stage where I am observing quasar spectrum, I have to filter through color selection of quasar candidates. So it's not completely obvious that outflows, what influence they will have on the quasar colors. For example, this quasar, if there is strong outflows are present, the quasar may not be in the color cut one applies to in SDSS, for example, they apply R minus I and G minus R colors. A quasar may not occur there. Actually, the quasar with outflow may be moved out of that because of colors are not matching. So that's why it was interesting when you go through radio detected quasar or you go through X-ray detected quasar, the fraction of BAL is much higher. Okay. We used to think 10%. Now, for example, BAL quasar, now people are thinking up to 40%. So I will not answer, it could be related to selection bias. One has to address that.
Maybe a stupid question, but I just wanted to know that do you see similar absorption features for Seaford galaxies and the quasars, or is there a difference? Can you comment on that?
What do you mean by similar? I don't find similar absorption features between two quasars.
Okay.
So it is difficult, but one thing one can say is that what you are asking is that whether ionization states are same? Yes. Whether you find the same species, carbon 4, nitrogen 5, oxygen 6, we find. Do you find the same thing like partial coverage? Yes. Do you find the signatures of line locking and you tell that it is radiation driven? Yes. But what is interesting is that the maximum velocity one sees in Seaford galaxies are relatively lower compared to the maximum velocity you see in quasars, which may be in some sense related to the availability of luminosity itself. It's not a direct correlation. We find a lower envelope of the maximum velocity versus luminosity. The same luminosity you can have range of velocities, but in the case of high luminosity, there is a high chance that you can also have very high velocities, which is not seen in Seafords. So physics-wise, they may be same.
Okay.
But because of powers, the values may be different. Have I answered your?
Yeah.
If you say the structures, they can be anything. But if you take a overall physics, one can find a unifying theme. Okay. So you can build one model for Seaford and apply that to quasar without bothering too much. It will work.
Okay, thank you.
So what's the Eddington ratio, L over L Eddington for these guys?
In this one,
Range.
they are exactly like quasar range, whatever you have. There is no
10 to the minus 3 and higher?
higher. I can give you this number. I have.
Any more questions? I have one. Nobody has any. No, I can talk like this. Do you see some correlation or anti-correlation between collimated outflows versus winds in these?
You mean that you
eyes?
look at the radio loud?
Yeah, so do
this
you
is one
see-
project we have started, and we asked for time for VLBA.
Okay.
So we said like it is useless. Your project is rejected, but somebody else have done that. So now we know the results. I think there is no correlation. But there are two things which is puzzling. One thing is that there is a strong correlation between spectral index and the occurrence of this. It seems that the steep spectral sources show the detection rate which is very different from the flat spectrum sources. That is one thing. For example, a CSS kind of source, there is a high probability. So you would expect some VLBA to show up something. That's what our proposal. We want to see like whether we can go to VLBA scale and see whether disturbed morphology or orientations. Can one use as orientation and see like whether it is the polar or equatorial thing?
Right.
Or if you say that it is nothing to do with that, but it is something to do with the disturbances, disturbed morphologies, it seems that you have in radio at VLBA scale you find all of them. Only clear discrimination comes from the radio spectral index. But the spectral index is the problem. You don't measure the spectral index at the same time. So this is one of the project one can try when you have a bigger bandwidth where you can do high frequency ranges simultaneously, or within a day if you can do 250 megahertz one, it's better to do at high frequencies because your turnaround will be there. And
No, the reason I asked was because in X-ray binaries, I think there's a well-known anti-correlation, right? When you have winds, you don't have jets and all. But only recently, I think in Cygnus A, there's work by Chris Reynolds who found that there were indications of both a very powerful jet and a wind.
yeah.
So that was, I think, the only case we know actually where they can coexist.
Because I think this is one of the things we are searching.
Okay.
So to start with, there weren't enough radio loud ball quasars. The other thing which we tried recently is to ask this question. I showed you these things, right? These clouds appearing and disappearing. See, this cloud is no more there. In black it is not there, in red it is there. So first 6 objects which we detected all were radio loud. So I came up with the idea that this may be the jet which is making this cloud disappear from the line of sight, right? So we found a fraction in the beginning when we started. The fraction was very high. 40% of the monitored radio loud quasars were showing this.
I see.
Whereas it was 2% reported in the literature. It was only 2% in radio quiet ones.
Right.
So I was almost writing a objet letter or something. Then I have a doubt that I want to make sure that this experiment is done in a controlled way, where all the radio sources were observed for 10 years, over a period of 10 years. These optical sources were observed for 3 years or something. So we went back to SDSS. For each radio source, we found quasars with same redshift, same luminosity, and made a control sample. And we also made a cut saying that we look at only objects which are monitored over this period. When you make this cut, you found that same fraction appear in optical also. Otherwise, it would have been an excellent result to say that even if jet may not be visible, the disturbance can, see, plasma goes. Plasma disturbance in this side can give whatever you call lateral motions. This is what we were after. I was very much excited. I told Kandu, he said like we should write a good paper, theory paper on this. The observation one has to wait at some time, then it was a sort of...
Right. Any more questions? Okay, if not, let's thank Srianand.